Welcome back to Engineering Acoustics. Hi, this is Professor Ryan Harne. In this video, we'll gather great intuition regarding how ultrasound is used in many practices of medicine.
So let's get started. We've learned a lot about transducer arrays so far when transducer sources or receivers are collectively gathered and their distribution is exploited. Transducer arrays are extensively used in medical practices, and it's oftentimes ultrasound that's used. In other words, acoustic waves at frequencies greater than 20 kilohertz. And this is due to the fact that we can propagate these waves, receive them, and synthesize them in computers very quickly to gain imaging and treatment capabilities in real time. Ultrasonic arrays are widely used for imaging, whether of newborn babies or other cancer treatment purposes. They're used in therapy, drug delivery, and much more. So let's gain some intuition about what is undertaken when we use transducer arrays for these medical practices. Let's start with ultrasonic imaging. The whole basis of ultrasonic imaging is to transmit and receive ultrasonic waves, and we decode images on the basis of the received ultrasound. Take, for instance, this case where we're imaging an eyeball. The ultrasound is radiated through the eyeball, and then echoes come back and are received by the same transmitter. So we have our sent signal and reflections. And these are all detected by the same device. Each reflection is due to an interface of the tissue, which tells us something about the shape of the tissue in the body. The first step is to take the absolute value of our voltage time series, and then apply time gain compensation due to the fact that the ultrasound is attenuated as it travels. So the reflection that's heard the last needs to get the greatest amount of time gain compensation. Then, knowing that waves travel at approximately 1540 meters per second in tissue, we can change this time axis to an x distance axis, and then correspond the voltage amplitudes to a brightness level. So how do we go from one line of brightness to a whole image? Well, knowing that ultrasound travels at a rate of 1540 meters per second in tissue, we know that the depth of any received pulse that's received at time t is given by the product of ct divided by 2, where depth is in meters. And this is due to the fact that we have to wait for the transmitted pulse to be received. Let's take an example where we have a 1 megahertz signal that's pulsed at 2000 kilohertz. So the pulse duration tau is equal to 1 divided by 2 kilohertz, which is equal to 500 microseconds. So every 500 microseconds, we send a 1 megahertz pulse. This gives us an axial or depth resolution of R is equal to C tau on 2. And in this case, R is 38.5 centimeters. So this is a theoretical limit on the axial depth resolution. In practice, the resolution will be less due to attenuation. Considering our example with imaging the eye, we take not just one line, but since our transducer array has many emitters, we take multiple lines. And this allows us to decode a range of these brightness lines. So naturally, we have in this example 7 brightness lines, but in practice, we recognize that our ultrasonic emitter is actually curved slightly. At the same time, the images where there are blanks don't make sense. So we have to blend in the images. This is one reason that when we see conventional ultrasound images in medicine, there's less resolution at the extremities than we have higher resolution close to the transmitters. How is ultrasound then used for therapy? Well, the fluids that carry the waves in ultrasound medical use are biological tissues. And this means that the fluids are oscillating, which means the tissues are oscillating. They're oscillating at the microscale, but the amplitudes will vary based on the wave intensity. And biological media absorb ultrasound, and this produces heat. For imaging, the peak acoustic intensities allowed by law are around 100 milliwatts per centimeter squared. This leads to very small fluctuations in the biological media, which are ideal for imaging. For therapy, the intensities are greater. They're around 1 watt per centimeter squared. And this increases the temperature of the tissue and relaxes muscle. But for other treatments where cell necrosis or death is desirable, the intensities may increase up to 100 to 10,000 watts per centimeter squared. And what is this basis for heat absorption of the biological tissues? The Bioheat transfer equation governs how the temperature change results from biological absorption of ultrasound. The temperature change in units Kelvin is computed according to the BHTE, Bioheat transfer equation. Conceptually, given all of these terms, the Bioheat transfer equation states that the temperature change is equal to the heat conduction minus heat perfusion plus a heat source. And the heat source, Q, is proportional to the total PRMS squared from an array. And the BHTE is central to our understanding of how to exploit temperature elevations in biological tissue. There are multiple practices where we wish to deliberately increase the temperature. For therapeutic use, small temperature increases occur, and these lead to relaxed muscle, increased blood flow, enhanced metabolism, and small gas bubbles that will result in the tissues that reduce swelling and pain. For therapy, these are unfocused transducers so as to not excessively expose the tissue to ultrasound. But focused transducers are used for treatment. The aim here is to increase the temperature so much that cell necrosis occurs, and this is often used for cancer treatment. The result of a focused space of ultrasound is often this teardrop shape, where the focal point is burnt out, but the areas immediately behind the focal point are also burnt out due to both the remnant of the focal field and also conduction that occurs from adjacent tissues. High-intensity focused ultrasound is the practice of using these concave focusing transducers to focus ultrasound so greatly that it burns out cancerous cells, and it leaves a pretty defined border between the diseased and the healthy tissue. This is a very low-cost, non-invasive, and successful treatment for prostate cancer so far, but it's only just beginning to receive FDA approval. HIFU by Sonoperation Medical is FDA approved for prostate treatment, but there's considerable research underway to apply HIFU to address other cancers. This focused ultrasound is used in other areas as well. It's used for sonoperation and drug delivery. So in our body, drugs are absorbed into the cells through their membranes. And ultrasound can promote temporary pores that open up in the cell membranes, and this is called sonoperation. Microbubbles are used to stimulate these pores, and they occur by ultrasound-based oscillation near a membrane. When a microbubble is in the body, ultrasound is focused to the microbubble, which causes the microbubble to fluctuate and oscillate, and it's pressed up against the membrane. So for instance, in a case of pushing open a pore, The microbubble is stimulated by the ultrasound. It pushes open a pore, and drugs that are in the environment adjacent to the microbubble can flow in to the cell. In the case of pulling open a pore, the same principle holds, but rather than directly mechanically forcing open a pore, the pore is created through the vacuum adjacent to the microbubble oscillation. And an additional use of sonoperation occurs when we translate the bubble. We cause the bubble to shrink so much that it is actually able to pass through the cell membrane. In this case, the bubble is filled with the drugs, and once inside, the bubble will break and then release the drugs into the cell. So let's summarize what we've learned. We've learned that ultrasound is extensively used in medical practices ranging from imaging, therapy, treatment, and drug delivery. It's the intensity of the ultrasound that determines how the biological media will respond. Imaging is conducted in a very linear regime where the small fluid particle oscillations of the tissue create reflected and scattered wavefronts that we thereafter decode into an image. For the more intense acoustic fields that are created by focused ultrasound, biological media heats up, and we tailor that thermal rise for our application.
That's it for this video. We now know that wave propagation at interfaces is central to imaging in medical ultrasound. In the next video, we'll dive more deeply into how waves interact when they come upon interfaces.